In this video, I will give you an overview of the multipole expansion, and this is another approach that you can use to find the potential from a charge distribution, and also once you have the potential, you can find the electric field and the electric force. So, I'm gonna start with the basics. I have here a charge distribution, and I have set the origin of my coordinate system to be here. This is O. I want to find the potential here, right here. So the position vector of the observation location has the tail at the origin and of course the tip at the observation location. This is where I want to find the potential at. Now, I know what the potential is from a point charge, 1 over 4 pi epsilon naught, a charge q over the relative position vector from the source to the observation location. So the vector r is defined r obs minus r source. This is so this vector r has the tip here and the tail here. Now, the process that I use when I have a charge distribution, I will cut it into small pieces. I'm gonna take an arbitrary piece, delta q sub I, and then I will make the assumption that this is a very small piece, so I will use the expression for the potential from a point charge, and I will find the potential here due to this delta q that I'm assuming behaves as a point charge. And then once I have that contribution to the potential, then I will choose another small piece, delta q, and I will do the same thing, find the contribution to the potential here and move on to the next one and so on until you have covered the entire charge distribution. Now, in one equation, this is potential equals the sum over I, 1 over 4 pi epsilon naught times delta q sub I. This is the I piece from my charge distribution over the relative position vector sub I, and this will be the vector that goes from source to the observation. Now, we have seen this already. In the case where I make the number of small pieces infinite, the sum becomes an integral. So I have 1 over 4 pi epsilon naught, the integral over dq over r. Now, in the next step, I see that I have here 1 over r. And now I'm showing you what is the relative position vector. It goes from the small piece delta q or dq to the observation location. Now, I'm using the law of cosines in this triangle over here. This is the angle alpha. I'm using the law of cosines to write this relationship. This side of the triangle, r squared, is equal to r obs squared plus r source squared minus 2, the product of the two times cosine alpha, where alpha is this angle over here. Now, in the next step, I'm taking r obs squared out as a common factor, so what I have left is 1 plus r source squared over r obs squared minus 2 r source over r obs times the cosine of alpha. Now, here's the thing. I'm going to call this as epsilon, and you will see why. So the relative position vector r, which is what I need when I do the integral, okay, this is here, the vector r, the relative position vector, is r obs squared. So this goes from the origin of the coordinate system to the observation location times 1 plus epsilon. If I can say that this thing here, that I call epsilon, is small, and when I say small compared to what? It has to be compared to the number next to it. So if I can say that epsilon is small compared to 1, then it is safe for me to say that the relative position vector whose magnitude I need in the integration is really just a little bit different from our obs, the vector that goes from the origin to the to the observation location. Now, these two would be exactly the same, of course, if epsilon was 0. But the further away you go from the origin, the more different epsilon will be from 0. Now let's take a look. I said that if I can say that epsilon is small and small compared to 1, if you see here in the numerator for the definition of epsilon, I have our source, which is this vector over here. In the denominator, I have the magnitude of the observation position. So that one goes from here to here. In order for epsilon to be much less than 1, what I need to have is that our obs is much greater than our source. Okay, this will allow me to say that epsilon is much less than 1 if you take a look at the numerator and denominator. Now, how can I accomplish this? Well, there are two ways. Either you make our obs really large or you make our source really small. Making our obs really large means that your observation location needs to be very far away from the charge distribution. The other approach to make our source very small means you need to have a very small charge distribution, or the size. What I mean small, I mean the size. The spatial size, the volume that it takes needs to be small. If you can trick that, if you can make it small, then it will be true that epsilon is much less than 1. Now, you have to, okay, and this is important and it is often forgotten. Everything that follows from now on takes place under this assumption. You cannot forget that the multipole expansion includes the assumption that epsilon is much less than 1 or our obs is much greater than our source. Meaning, if you are very close to a charge distribution, this approach cannot give you a meaningful result. Alright, we're moving on. Now, I have, so I say that this is, I call these things over here as epsilon, and that allows me to write 1 over r. So essentially I'm taking the square root and then the inverse of the left side and the right side. Square root and inverse. This gives me 1 over r equals 1 over r obs, so square root and inverse, and then times 1 plus epsilon to the power of minus 1 over 2. And as I said, I have epsilon much less than 1. Now, when epsilon is much less than 1, I can do an expansion. We know that when we have, and we call this the binomial expansion, when I have a plus x to the power of n, the binomial expansion is given by this expression. When you apply it to when a is 1 and x is epsilon and n is minus 1 over 2, what you get is this. This is the binomial expansion. If you apply the binomial expansion to this specific term, then you will get this. And plus, I forgot to write here. Of course, you have more stuff. but I just did not write them. So I get this for 1 plus epsilon to minus 1 over 2, and then okay, from now to go from here to the next step, there is a lot of algebra, a lot of moving stuff around and so on. And the way to go from this step to the next step, you go back and you see wherever you see epsilon here, you use what you actually defined epsilon to be, and you rearrange terms, and as I said, you do a lot of algebra until you reach this 1 over r, which is what you need in the integration, is equal to 1 over r obs times an infinite sum. And of course we also encounter the Legendre polynomials, and now you take 1 over r, you take this expression for 1 over r, and you plug it into the integral that I have over here, and this gives us the potential as 1 over 4 pi epsilon naught, an infinite sum of 1 over r obs n plus 1 of the integral of r source to the power of n times the Legendre polynomial of cosine alpha, and you're integrating over dq, meaning you're integrating over your charge distribution. Now, possibly that will be a volume charge distribution, so you will say that dq is rho dv, where this little v is the volume, okay, not potential. So this is this infinite sum is what we call the multipole expansion. Now, it is an infinite sum. The first term, the n equals 0, is what we call the monopole. If your charge distribution overall has a charge, meaning it's not neutral, then you will have a non-zero monopole term. Now, if your charge distribution is overall neutral, then you will find the n equals 0 term to be 0. For n equals 1, we get the dipole term. And for n equals 2, we get the quadruple term, and so on. Now, because this is an infinite sum, this means that the more terms you keep, the better your approximation for the potential is at the observation location, which makes sense. If you want to get a very, very rough estimate of what the potential is at your observation location, try the first term and see what it is. You get a 0, then move on to the dipole. Calculate that. If it's not 0 and you're okay with what you got, then stop there. If you want to improve, though, your approximation to the potential, then keep adding, keep calculating more terms to using the multipole expansion expression. And to summarize, remember, when you use the multipole expansion, remember that there is a very important step over here, that we use the binomial expansion, and we made the assumption that epsilon is much less than 1. Okay, this is part of the multipole expansion theory. Just keep it in mind whenever you use it.